Welcome to the Chemistry 221 Exam 1 review. I'm glad to have you here. The purpose of this video is to go over some problems that we would have done during the normal face-to-face lecture, where we would have had typical problems that you might see on the midterm exam. And what I would do in the regular class is we would have eye clickers that we could use to respond. You could try and see like how you're doing on the questions. And after a short amount of time, then we talk about the answer. So it's a good way to kind of check yourself and see how you're doing. Now in this virtual format, it's going to be a little bit different, but what I will do is I will post some questions. I'll talk about it a little bit, and then I'll have a place where you can pause the video. And I encourage you to work on the problem yourself. And then when you're ready to see how you did, start the video again, and we'll go over the answer and stuff like that. This is all a time for you. All right. You can get as much or as little out of this as you want. And again, you can use this in any way that you desire. I'm just trying to help you prepare basically for the midterm exam. In this virtual world, if this is an online class, midterm 1 will be over chapters 1, 2, and a little bit of chapter 3. It's basically up to chapter 3, section 3.2. All right. The exam itself will have 20 multiple choice questions, and they always have 3 to 4 short answer questions. That number kind of varies depending on the format of the exam, but 3 to 4 is a good way to do it. The 20 multiple choice questions, each of those will have 5 possible answers, and only one of the answers is correct. The short answer questions, please show your work. I want to see how you set it up and how you get to the final answer. And if you'd circle your final answer, it makes my life a lot easier. Multiple choice questions are either right or wrong. There's no in between. But with the short answer questions, you can get partial credit if you show how to set things up, things like that. Even if you don't know how to finish the problem, definitely put something down. You might get some partial credit, which is cool. Now, if this is an online class, the midterm will be due by Friday at 9 a.m. via email. And if there's questions about this, please email me directly and I can help you fill in more details and stuff. But regardless, after you turn it in, I'll grade it. And within a day or two, I'm going to be a little flexible on the date, but within a day or two, I'll return your midterm exam to you. And the very last page will be a summary sheet saying how you're doing in the class as of this time. And I encourage you to check that out. If you're missing any labs, I'll make sure that I've circled the labs and try to get the labs into me. Those are a pretty good point thing, especially with the lab completion bonus. And of course, you can see how you did and make sure that the scores I have for you are the ones you actually got. Sometimes I hate to admit it, but I do make mistakes, so double check. So without further ado, I wish you good luck with your studying, and let's start the review. In this question, we have a piece of metal with a mass of 33.2 grams, and we place it in 10 milliliters of water in a graduated cylinder. And you can see in the little picture there, there's kind of a before and after picture of what's going on. So notice on the left side, or in the middle, I guess, it says 10, that's where the water goes up to, 10.0 centimeters cubed. And after putting the metal in, the water level rises to 22.3 centimeters cubed. Using all this information, determine the identity of the metal. And you can see a list there of different metals and their densities. So really what I'm asking you to do here is find the density of the metal, and then you can compare the density to the one that's closest in that list to find the identity. So see if you can do that. So at this point, pause the video, and when you're ready, then you can unpause and start up again. Okay, I'm going to assume that you now have the problem done and you're ready to talk about the answer. And again, if you haven't done the problem yet, again, I encourage you to pause it, work on it, and then see how you did. But anyway, if you are ready to rock and roll on this one, this is a density problem, all right? And density is mass over volume. The mass is usually represented in grams, and volume can be in milliliters or centimeters cubed. Milliliter is equal to a centimeter cubed, so there interchangeable. Now, the volume that the metal takes up can be found by the difference of the water volumes. So you can see the water started at 10.0, it went up to 22.3. So 22.3 minus 10, or about 12.3 centimeters cubed, that's going to be the volume. That's going to go in the bottom of your calculation. And in the top part, you want to put the mass of the metal that caused that volume displacement. That's the 33.2 gram number. So in this calculator then, 33.2 grams divided by parentheses, 22.3 minus 10, parentheses, or just, of course, 12.3, and you should come out to answer E, about 2.70 grams per centimeter cubed. And if you called it 2.70 grams per milliliter, that's fine. A centimeter cubed and a milliliter interchangeable, no big deal. Cool. Here are some temperatures that you can find on different places on the Earth. 29 degrees Celsius, 45 degrees Fahrenheit, and 256 Kelvin. And I'd like you to put these three temperatures in order of increasing temperature. So the coldest first and the warmest, the hottest one would be last. And so what this question is asking you to do is basically convert the different temperatures into a common unit. Now remember that to go from Kelvin to Celsius, Kelvin values are never negative, but Celsius values can be. So what I would do on this problem is convert Kelvin to Celsius. I would take 256, subtract the 273.15 number, and that's going to be that value in Celsius. So you can convert 256 Kelvin to Celsius. Then I would do the same thing with Fahrenheit. Now Fahrenheit, the temperature in Fahrenheit equals 1.8 times the Celsius temperature plus 32. So to get the Celsius temperature by itself, you would first take the Fahrenheit value and subtract 32, and then whatever's left over, you would divide by 1.8. So see if you can do this on your own first. And again, this is going to be a good place to pause the video. And when you're ready, you can unpause and we'll talk about the answer. I'm going to assume you have worked on the answer and you're ready to see how you did, and that's totally cool. The game plan in this is I would convert Fahrenheit to Celsius and Kelvin to Celsius. If you wish to convert everything to Kelvin, that's fine too, or everything to Fahrenheit, but Celsius is kind of the intermediate part. That's just my recommendation. Now, 273 Kelvin is 0 Celsius, and that temperature is lower than 273. That's pretty cold. All right, so 256 sounds like that's going to be the coldest. On the other hand, 45 degrees Fahrenheit. Now, if you grew up in Oregon, where we use Fahrenheit all the time, 32 Fahrenheit is freezing. That's where water freezes. And so 45 isn't too high above that. So I think that 29 Celsius, that sounds pretty warm to me. So you can sometimes use just kind of general explanations here for what's going on. Of course, the best way would be to solve it. So let's look at this. The answer, by the way, is D, and the Kelvin temperature is the coldest in that list, followed by Fahrenheit and followed by Celsius. But here you can actually see the values converted. So this first part right here, we're taking the Kelvin temperature, 256, and subtracting 273.15, cut it off at the ones spot. That's this sig fig thing to do. So you get negative 17 degrees Celsius, and that is certainly colder than 29, so that's a good number to have. Now we need to convert the Fahrenheit into Celsius as well. So you can see here's the Fahrenheit temperature. You subtract 32 first, then you divide by 1.8 or 9/5, either way. Anyway, that temperature comes out to be 7.2 Celsius. So it's warmer than the Kelvin's negative 17 Celsius, but certainly less than the 29. So that's why answer D would make the most sense here. This question is about length and metrics. All right, we've got 4 lengths here: 215 millimeters, 9 centimeters, 2.3 meters, and 0.125 meters. And it says put these in order of increasing size. So smallest to largest is what you want to do. Now, there's a whole bunch of different ways to solve this problem. I would probably convert things to meters. You already have 2 meter values. So if you can convert 215 millimeters to meters and 9 centimeters to meters, that would be, I think, the less work. Of course, you have to know about the metric prefixes. So milli is 10 to the minus 3. So that means that a millimeter is 10 to the minus 3 meters. Alternatively, of course, you could use 1,000 millimeters equals 1 meter. Either way is fine. Now, centa, C there, centa is 10 to the minus 2. So a centimeter is 10 to the minus 2 meters. You could also use 100 centimeters per meter. But either way, see if you can convert those over, put them from smallest to largest. This is a good place to pause the video, and when you're ready, unpause it and we'll look at the answer. Okay, I'm assuming at this point you want to look at the answers to this question, and that's fantastic. Again, the punchline here is put them from smallest to largest. And I would put things in meters, all right, because you've already got 2 of them meters. You only have to convert 2 of them, but you can convert them all to any unit you want to. Going from millimeters to meters, you want to basically divide by 1,000 or multiply by 10 to the minus 3, either way. But you want to move the decimal point 3 positions to the left. So 215 millimeters becomes 0.215 meters. And you can see that that is bigger than 0.125 meters, but not as big as 2.3 meters. 9 centimeters, you want to divide by 100. There are 100 centimeters per meter, and that will tell you the number of meters. So dividing by 100 means essentially moving the decimal 2 to the left, 0.09. So in this problem, 0.09 meters or 9 centimeters is the smallest, all right? Then 0.125 meters is the next biggest one. Then 0.215 meters or 215 millimeters is next, followed by 2.3 meters. So this is a great question just to kind of check yourself, see how you're doing with those metric prefixes. In chemistry, remember, the centa and milli are 2 of the 5 really important metric prefixes you need to know. The other 3 are kilo, micro, and nano, and we'll see all of those throughout the course. Kilo is 10 to the 3, micro 10 to the minus 6, and nano 10 to the minus 9. Here we have 5 different symbols, all right, for elements. And the number in the superscript, the first number, that's the mass number. And the number in the subscript, the second number, if you will, that's the atomic number. So the question is, which of the following is not an isotope of element X, where Z equals 9? So look at those values and look at your knowledge of an isotope and see if you can figure out which one it is. And pause the video at this point, and then when you're ready, you can unpause it. Okay, I'm going to assume you're ready to go here. An isotope is an atom with the same number of protons, the same atomic number, but a different mass number. Mass number is protons plus neutrons. So isotope have different number of neutrons, but the same number of protons. And it's the subscript, the number, the second number in those things right there, which is the atomic number. So if you look, all of them have a 9 there except for B, all right? And those 9s are the atomic numbers. That's the Z value, Z equals 9. So number B there with 10 protons is not an isotope, all right? 10 would be a different element. If you change that number, that atomic number, you're changing the element. So number 9 on the periodic table is fluorine. So A, C, D, and E are all isotopes of fluorine. 9 protons, They all have a 9 in that lower left kind of value right there. So those are all fluorine. But number B there with a 10 in it, that's not fluorine. That's going to be neon. If you look on the periodic table, number 10, atomic number 10 is neon. So B is definitely not an isotope. The other ones are isotopes. Which statement below describes the composition of a neutral atom of iron 58? In this question, you can see there's neutrons, protons, and electrons, and the first 4 answers. And I want to test your knowledge of what it means to be neutral, and also what that dash 58 means after the iron. So try this problem out, pause the video, and when you're ready, just unpause it, and we'll talk about the answer. I'm going to assume at this point that you have worked on this question and you've got an answer, so let's see how you did. The first part of this question says we have a neutral atom, and a neutral atom can only happen when the protons and electrons are equal to each other. So if you look at these particular answers then, 2 of them right away are not going to happen, all right? In A, you have 32 protons and 26 electrons. There are more protons in A than there are electrons. That, whatever A is, that's going to be very, very positive. More protons than electrons means positive. So answer A is not going to happen. The other one that's not going to be neutral is C. If you look, that one has 32 electrons, 26 protons. That has more electrons than protons. That's going to be a negative ion. That one's not going to be neutral either. So our answers here are either going to be B or D, or possibly E, and I'll be honest, it's not going to be E. So let's think about now what the iron 58 part means. Iron on the periodic table is number 26, and like we talked about earlier, 26 is the atomic number, and the atomic number represents the number of protons. So in both B and D, there are 26 protons. Those are both going to be iron atoms and stuff because they've got protons. And because B and D both have 26 electrons, not only are they iron, but they're going to be neutral. So the last thing we need to do then is think about what the 58 means right there. 58 is the mass number, and it equals the protons plus the neutrons. So we have to figure out a combination then of protons and neutrons and B and D, which are going to be equal to 58. And 26 plus 26 on answer D, I think, is 52. So I'm going to think then that the answer is B. And it is 26 protons plus 32 neutrons is 58, all right? And that's where the 58 comes from. So if you have a neutral atom of iron 58, you're going to first of all have equal protons and electrons. Iron always has 26 protons, so that means 26 electrons as well. And then finally, the 58, to figure out the number of neutrons, you would go 58 minus 26, and that's where answer E comes in. So we have enough information to answer this question. Absolutely, it's answer number B. Cool. An element E has several naturally occurring isotopes with the following abundances. So we're just listing them as some random capital E. All right, don't worry about that. But notice there that 72E is about 54.5%, 73E is about 15.6%, and 74E about 29.9%. And the question then says, the most reasonable atomic weight for this element would be, and it lists 5 possibilities. So see if you can think about what the percentages mean when coupled with their mass number, and how those two go together to find the atomic weight, which is essentially an average of all the masses of the different isotopes. So this is a good place to pause your video, try this problem on your own, and then in a little bit we'll start up again. Okay, I'm going to assume that you've worked on this question and you've got an answer. You want to check it out, and let's do it. When it comes to isotopes, all right, sometimes one isotope is more abundant than the other. And if you look at those three isotopes listed, the 72E, that's more than half of all the different isotopes. That's more than 50%. So the atomic weight is just an average of all of them. And because 72 is more than half, that means that the atomic weight, the average, will be somewhat close to 72. All right. It's not like it's 90% 72, but it is more than half. So the atomic weight, the average, will definitely sway more towards 72. But you do have an appreciable amount of both 73 and 74. All right. It's not halfway up, but it is quite a bit. So having an answer of 72.1 in A is probably a little too enthusiastic. Like if we had 90% 72 and maybe just a little bit of the others, that would make sense. But that's probably too much. On the other hand, 73.4 and the bigger ones below it, those would imply that you had high abundances for isotope 73 and 74. And they're just not that big compared to 72. So I would argue in this question that probably answer B is the right one. But wait, Dr. Russell, I want to do it a math way. I don't like your hand-waving ways. Oh, good. Whoever said that in the back of the classroom. This is a stupid thing I do sometimes in lecture. But anyway, babbling. If you don't like my hand-waving way, which is kind of what I was doing there, you can also do it the math way. And that's what this part is down here. Now, you can take the decimal version of those percentages. So 54.5 would become 0.545. And 15.6 would become 0.156. You take those decimal versions and you multiply them by their mass, all right? So 0.545 times 72, because that's the mass number of that isotope. And you do the same thing, 0.156 times the 73, the same thing, 0.299 times 74. Add those numbers together and you end up getting to 3 sig fig 72.8, all right? So that's an alternative way to do that. So these kind of questions have two ways. If you think about what it means to be an average, you can a lot of times kind of work your way through it. But this math way works really, really good too. The symbol right there, which is a sigma, that just means add up all of them. And that means add up all of the abundance, that's what the decimal version of the percentage is, times the mass of that particular isotope. So like times 72 times 73. Either way works great. You work with the way that works better with your learning style. Here's a list of 5 ions, and the question is, which of these is not likely to form? So look at those 5 possibilities and also think about your knowledge of the positive metals and what they like to be, and see if you can find the correct answer. This is a good place to pause the video, and when you're ready, just unpause and we'll talk about it then. Okay, I'm going to assume you've worked on this question. That's totally cool. Now, first of all, notice that these are all metals, and metals always like to be positive. So that part is good. All right, if you saw a metal which was negative, that would be less likely. A lot of metals on the periodic table are what they call fixed charge metals, and that includes a couple on this list. The fixed charge metals are group 1, group 2, and the stairs. All right, Group 1 or Group 1A metals always like to be positive 1. So that would be, for example, like sodium. Sodium is in Group 1A or Group 1, depending on your periodic table. Number 11 on the periodic table is Na, and that's in Group 1. And all of those metals like to be plus 1. And that's really all we ever see. So we don't see sodium as plus 2. We don't see potassium below it with a plus 3. We always see sodium as plus 2. The stairs are the weird 6 elements that I talked about in lecture, and 2 of the atoms on this list are part of the stairs, and that includes aluminum and that includes zinc. So if you look at the aluminum, which is number 13, aluminum, gallium, and indium, AlGaN, that's the 3rd step of the stairs, and those metals always plus 3 for our uses. Then right next door, Zn, which is answer E, and cadmium, that's the second step. Those metals are always +2. And then silver, Ag, which is the first step, that is always a +1 metal. So the stairs are also fixed charge metals, all right, and those are legit. Now, iron is a variable charge metal. It's number 26 on the periodic table, and variable charge metals are difficult to predict. So iron +2 is as reasonable as anything. It doesn't seem unreasonable, but really what I want you to look at here is answer B, because magnesium is a group 2 or group 2A metal, and those guys always want to be +2. You will very, very, very rarely find magnesium +3 in a lab. If you're in a vacuum in a high energy kind of environment, yeah, maybe you could make magnesium 3+ for a little bit, but in the wild, in nature, when you're farming this out, magnesium always +2. So just like sodium is always +1 in group 1, magnesium always +2, you shouldn't see +3. When the ion strontium 2+ forms, then there's 5 different statements, and one of those statements is correct and the other 4 are incorrect. See if you can figure out which of those statements is correct. Pause the video, and when you're ready to hear the answer, then unpause it and we'll talk about it. Okay, I'm assuming that you're ready to look at the answer, which is fantastic. Now, strontium is number 38 on the periodic table. It's a group 2 or group 2A metal, and those metals love to form +2. Now, strontium number 38 means that it has 38 protons, and 38 protons means then that a neutral strontium would have equal number of electrons, would have 38 electrons. So neutral strontium would have 38 protons and 38 electrons. And if you make a +2 ion, you are going from neutral strontium, just Sr, which is a metal, if you look on the periodic table, you're going to make strontium with a +2 charge, and those 2 electrons are kicked out. Now remember, in neutral strontium, 38 protons, 38 electrons, that's what neutrality is. If you lose 2 electrons, then you still have 38 +1 protons, but only 36 -1 electrons. So 38 minus 36 essentially is where the +2 comes from. Those 2 electrons are lost, more protons than electrons, that becomes a positive ion. So some of these here say something about 1 electron. That's not going to happen. If you have strontium, you're going to be losing 2 electrons. You're not losing 1 electron to make a +1 strontium, you're losing 2 of them. The last one, E, is also not right. If you lost 3 electrons, the strontium would have a +3 charge, and you certainly don't have that. So it comes down to C or D, and if you look carefully at both of those, one says loses and one says gains, all right? In this particular problem, strontium is definitely losing the electrons to become positive, all right? If strontium were to gain 2 electrons, then you'd go from 36 protons and 36 electrons to 36 protons and 38 electrons, and 36 times +1 plus 38 times -1, that would give you a -2 strontium ion. And that's not how that flies. So definitely the answer here is going to be C. It's losing 2 electrons, it's becoming positive, and it does have the same number of electrons as krypton. If you only have 36 electrons, that's the same number of electrons that neutral krypton would have. That'll be important for us later on. We'll talk more about that in a future lecture. One of these formula and name combinations is not correct. See if you can find out which one it is. This is a great place to pause the video, and when you have your answer, then you can unpause it and we'll talk about the answer. I'm assuming you have this problem figured out and you want to talk about it. So this question is basically about how to name compounds and get names from formulas to names. A lot of these have polyatomic ions, and you know that because the formulas have more than 2 types of atoms. So the first one has calcium, sulfur, and oxygen. That's 3 types of atoms. That means you've got a polyatomic ion. And SO4 minus 2 is the sulfate ion. Calcium is a group 2 or group 2A metal. It wants to be positive 2. So positive 2 calcium with negative 2 sulfate, they go together 1 to 1. Answer A is okay. It's not a problem. Calcium sulfate is CaSO4. Now, the second one, do you have a polyatomic? Well, let's check. Sodium, Na, nitrogen, and oxygen, that's 3 types of atoms or more, so that means, yep, there's going to be a polyatomic ion here too. And the polyatomic ion is NO3, which is nitrate. Nitrate is NO3 negative 1. Sodium in group 1A likes to have a positive 1 charge, so they go together 1 to 1. This is sodium nitrate, and that's a correct formula. Everything's okay on B2. The third one, we have magnesium and we have iodine. 2 types of atoms. Does this have a polyatomic? No. You only have 2 types of atoms, magnesium and iodine. So this does not have a polyatomic. This is a regular kind of compound. So iodide in group 7, 7 minus 8, iodide likes to have negative 1, and there's 2 of them there. Magnesium in positive 2, in group 2A will have a positive 2 charge, so you will need 2 negative 1s to balance the magnesium. C is okay. Now, on D, let's count the atoms. Nitrogen, hydrogen, phosphorus, oxygen. 4 types of atoms. You could, and you do, have 2 polyatomic ions here. Ammonium and phosphate. And the NH4 is the ammonium, and the phosphate is PO4. But the problem here is that phosphate has a negative 3 charge, and ammonium, one of the few positive ones, has a positive 1 charge. So if you put a single positive 1 ammonium next to a phosphate, you're not going to get a neutral compound, something without a charge. And that's really important in this section, to have things that are neutral. So ammonium phosphate is not NH4PO4. Ammonium phosphate would have 3 positive 1 ammoniums to balance that phosphate. So the formula would be parentheses NH4 parentheses 3 PO4. That would be the formula for ammonium phosphate. That way the 3 positive 1 ammoniums will balance the negative 3 phosphate, and you'll be good to go. So answer D is obviously the answer. Now, the last one there, just for completion, you do have calcium, chlorine, and oxygen, 3 types of atoms. Yes, you have a polyatomic ion. ClO is the hypochlorite ion, and it has a negative 1 charge. And just like in A, calcium will be positive 2, so you need 2 negative 1 hypochlorites to go along with it. Ca parentheses ClO parentheses 2 is the correct formula. Notice that we did not use parentheses in B, but we did in E, and also for the correct answer there on D. You only use parentheses if there's more than 1 polyatomic ion. If there's only one, like NaNO3 or CaSO4, do not use parentheses. That'll drive chemists, i.e. me, who's grading your assignments, all right, that'll drive all of us crazy. So only use parentheses if there's more than 1 polyatomic ion. Which compound in this list is not ionic? So this question is going to ask you exactly to think about what it means to have an ionic bond, and one of those is definitely not an ionic compound. So at this point, pause the video, and when you're ready, you can unpause it, and we'll talk about the answer. I'm assuming that you have the answer figured out, which is totally cool, and let's see how you did. Ionic compounds are compounds that are held together by positive and negative charges, and it's a very strong type of interaction. So far, we've looked at ionic bonds and covalent bonds. Covalent bonds, the electrons are shared amongst the different atoms. Ionic bonds are much stronger, but covalent bonds are more flexible, and you need those covalent bonds for a lot of things in life. But anyway, to identify an ionic compound, you have to have a metal with a nonmetal, or something that looks like a positive cation with a negative anion. So if you look through this list, lithium is a metal, aluminum, barium, sodium, those are all metals, no problem. And they're all with something negative. So chloride, fluoride, nitrate, -1, and either hydrogen carbonate with a -1 charge, or the carbonate ion, which is CO3 - 2. There's a lot of charges going on. Now, on B, sulfur is not a metal. It's a non-metal. It's above that metalloid line. The oxygen is called oxide because it's more in 2 electrons, and that'll be important to us later. But for right now, because it's a non-metal with a non-metal, answer B is not an ionic bond. In an ionic bond, you have to have a cation and an anion coming together. Sulfur and oxygen, 2 nonmetals, they would use covalent bonds. So again, to identify covalent bonds, you basically want to use nonmetals and nonmetals, while the ionic bonds will usually have metals and nonmetals. Sodium oxalate has the formula Na2C2O4. Based on this information, the formula for iron 3 oxalate is, and there's 5 different possibilities. Now, oxalate is a polyatomic ion. It's a little bit more rare than a lot of the ones we're looking at, but it's the same idea. So using, though, that formula, if you don't know what oxalate is, I think you can figure out what you need to answer the question, to figure out what the formula is for iron 3 oxalate. So try this problem on your own, pause the video, and when you're ready, unpause it, and we'll talk about the answer. Okay, I'm assuming that you've worked on the answer. You're ready to talk about the question. Very cool. Oxalate, as I said, is a polyatomic ion. And if you look at the formula for sodium oxalate, Na2C2O4, the C2O4, that's the oxalate. And sodium is with it. So if you don't know what oxalate is, and that's totally fine, by the way, sodium is a +1 metal. It's group 1A. It's a fixed charge. Sodium's always +1, and there's 2 +1 sodiums there in that formula to balance the C2O4. So C2O4 must have a -2 charge, and oxalate is C2O4 with a -2, if you look it up or if you knew that. So that's going to be important because we need to know what the charge is on oxalate to balance it with the iron 3. And iron Roman numeral 3 means that it's iron +3. So to make the +3 iron and the -2 oxalate balance, you can use crossover or you can use a common denominator, whatever you want. You should find that answer D is the correct answer. Iron +3 times the 2 of them there would give you +6, and 3 -2 oxalates would give you -6, +6, -6. Everybody's happy. You're good to go. So oxalate is -2, and if you knew that, well done. That's awesome. But if you didn't, you can figure it out. Okay, sodium's always +1, so oxalate has to be -2, and then take that -2 oxalate, balance with an iron +3. Good to go. All of the following statements concerning ionic compounds are correct except one of those statements in there is not a correct response. And I'd like you to try and figure it out. So this is a good place to pause the video. And if once you're done working on the question, then unpause it and we'll talk about the answer. Okay, I'm assuming that you have worked on the problem and you want to talk about it, and let's just see what's happening. Now, if you have an ionic compound, we're going to be thinking a lot about Coulomb's law. And Coulomb's law is a way to describe the attraction between positive and negative charges. And although we won't use Coulomb's law in like a way that physicists would use it, we will get two things from Coulomb's law. And the first one says that as the ion charges increase, then the attraction between the ions will increase. And if you look at the first one, A there, it says as the ion charges increase, the attraction increases. That one is true. All right, that's directly from Coulomb's law. The second one there says ionic compounds form extended three-dimensional networks called crystal lattices. That's also true. That's where the ionic strength comes from. These lattices go on in 3 dimensions. So like for sodium chloride, it would go sodium ion, chloride ion, sodium chloride ion, and it would go on and on, forward, backwards, left and right, and up and down. Very, very strong lattices, hard to break up sometimes. So B is also true. C, ionic crystals tend to be rigid and they cleave along the planes. I showed a picture in the lecture notes of a potassium bromide crystal, and you could actually see the very nice sharp lines and stuff that happen. This is very common for crystals. They will cleave along the planes of the ionic compounds and stuff like that. So I would answer that C. D, positive and negative ions are attracted to each other by electrostatic forces. Electrostatic forces is the fancy name for positive and negative, and that part is also true. So if A, B, C, and D are true, you can probably imagine E is going to be the bad one, but let's check it out. E says the electrostatic forces are weaker in calcium oxide than in sodium chloride. And I said earlier that there were two things we're going to get from Coulomb's law, and one was the number of charges. The other one actually happens to be the distance, but we won't talk about that. But that first one, the charges, calcium is a positive 2 metal, and oxygen, oxide, negative 2. And in sodium chloride, sodium positive 1, chloride negative 1. Now, calcium and oxygen have a positive 2, negative 2. That's kind of like a double handshake. And that's a lot harder to break up than this positive 1, negative 1 single handshake of sodium chloride. So if you reread A, as the ion charges increase, the attraction increases. Calcium oxide has much higher ionic charges. So E is the false one. E is not true. This is Coulomb's law, all right? And again, we're not going to use this explicitly, but the top part here is what I'm focusing on in this problem. In sodium and chloride, you have 1 positive and 1 negative, essentially. So 1 times negative 1 is like negative 1. On the other hand, for calcium oxide, in the top part, you'd have positive 2 times negative 2. That's a factor of 4. So the calcium oxide, much stronger forces. The other part about Coulomb's law, which will be important more to us later than now, is that as the distance between the ions gets larger, the force goes down. So distance increases, the force goes down. These two examples are about the same, but later on we'll come back to that, how the distance can really make a big difference. We have 0.25 moles of each of these following elements. Which one has the largest mass? And in terms of mass, what I would do for this problem is I would think about the largest number of grams. You will need a periodic table, I'll tell you that much. See if you can do this problem on your own first, and if you get stuck, no worries. Pause the video, and when you're ready to hear the answer, then unpause it, and we'll talk about it. Okay, at this point, I'm assuming you want to see how you did on your answer to this question, which is fantastic. So in this question, we've got 0.25 moles of each of these elements. Which one has the largest mass? Now, because we're starting with moles and we need to turn it into mass or grams, we need a way to go from moles to grams. And that is going to be the molar mass numbers from the periodic table. So as an example, on A, on my periodic table, if I look at iron number 26, the 55.845 number, that's the molar mass of that compound. So I could take 0.25 moles and multiply it by 55.845, and that would tell which one, how much mass was in 0.25 moles of iron. And I can do the same kind of thing for all those different ones. Now, molar mass, more or less, increases with atomic number. So aluminum, which is number 13, has a smaller molar mass than iron number 26. So we want the atom up here with the largest atomic number, and that's zinc. Zinc has a molar mass, or an atomic number of 30 and a molar mass of 65.38. So if you actually want to see how those numbers work out, those are the actual values. You can see that definitely the zinc here, about 16 grams, that's the mass of zinc from 0.25 moles, and that's larger than the other ones up there. Iron is close, but not quite as big as zinc. So this is a cool question just to make sure you understand what the molar mass means, stuff like that. This is kind of a fun problem. Well, okay, I'm a chemistry nerd instructor, so maybe this is just fun to me, but I'd like you to calculate the average mass of one chromium atom. Now, this at first is a little strange sounding, so I'm going to give you a couple of hints. First of all, chromium on the periodic table is number 24, and you will need the molar mass of chromium to calculate it. So remember, molar mass has units of grams per mole. You're also going to need Avogadro's number in this problem. And remember, Avogadro's is 6.022 times 10 to the 23rd. So for chromium, that would be 6.022 times 10 to the 23rd atoms per mole. And notice there how per mole was in both the molar mass and Avogadro's number. So if you can get rid of the moles, you're going to have grams per atom. Play with this a little bit, see if you can get a good answer. Pause the video, and when you're ready, just unpause it and we'll talk about the answer. Okay, I'm assuming you've tried this problem and you just want to see how you're doing, which is fantastic. So for a question like this, all right, you do need the molar mass of the element, and for chromium, that's about 51.996 grams per mole. You may have a different number on your periodic table, but about that number, okay? That's the grams per mole of chromium. But Avogadro's number says that in a mole of chromium, you're going to have 6.022 times 10 to the 23rd atoms. And in this question, you essentially want units of grams per atom, mass per atom, all right? So if you take thanks for playing. If you take the molar mass, 51.996, and divide it by Avogadro's number, that's going to be how you get this number. And it comes out to be 8.634 times 10 to the minus 23rd grams. So that's answer A. And again, on the bottom right here, you can see how this works. 51.996 comes from the periodic table. That's the grams per mole. You then essentially want to divide by Avogadro's number. The moles on the bottom and the molar mass are canceled by the moles in the top. When you divide by Avogadro's number, you end up with that very, very, very small number of grams per atom. Notice this nomenclature, e to the 23rd. This is another way of writing times 10 to the 23rd. And that's done because computers and sometimes calculators will use e23rd or e10th or something like that. That's totally fine to use your answers that way if you'd like to. Of course, the formal way is to write times 10 superscript minus 23, but you could write this answer as 8.634 e minus 23, and that would be fine. It's just an alternative way to write this, and those are all okay. Which answer best represents the percent composition of the compound CO2, carbon dioxide? Now, carbon dioxide has carbon and oxygen in it, and one of those sets of percentages best reflects the percent carbon and the percent oxygen in the compound. See if you can figure this one out on your own. Pause the video, and when you're ready, unpause it, and we'll talk about how to solve this problem. Okay. Okay, I'm assuming you've tried this problem and you want to see how you did, and that's fantastic. If you're asked to find a percent composition, percent by mass, percent by weight, etc., all right, they're all the same thing, but not percent by volume, but we don't do that in chemistry. So anyway, percent composition, percent by mass, percent by weight, they're all the same thing. What you want to do is first find the molar mass of your compound. So in this case, you want to find the molar mass of carbon dioxide. And carbon dioxide's molar mass has 1 carbon and 2 oxygens. Carbon on the periodic table is about 12 grams per mole, and oxygen is about 16 grams per mole, and there's 2 of them. So the molar mass would be 12 plus 16 times 2. It's roughly 44 grams per mole. And you can do a better job with your sig figs than I've just done off the top of my head, but that will be good enough for this discussion. Anyway, once you've found the molar mass, then that goes in the bottom of the calculation, and on the top you put the amount of the element in that you're looking at. So for example, for carbon, we had 1 carbon, or 12 grams. So we would, per percent carbon, you would have 12 grams divided by 44. 12 grams is how much carbon there was in the 44 grams per mole calculation we did. And for percent oxygen, you would take 2 times 16 in the top part, or 32, and divide by 44. So in this problem, here's the actual numbers worked out. And by the way, the answer is C. All right. So first of all, to more sig figs than I did off the top of my head, molar mass 44.01 grams per mole. And from that CO2 number, there was 1 carbon, 12.0. So 12.0 divided by 44.01, that comes out to be 27.3%. 2 moles, 2 times 16 is 32. So you do the same kind of thing right there. Percent oxygen, 72.7%. And if you've done this correctly, the 2 percentages together should equal 100%. So 72.7 plus 27.3 looks pretty awfully close to 100%. Another thing you can do is, if you had percent carbon at 27.3, why not just subtract that from 100%? That's an alternative way to find percent oxygen as well. So all of those are legit ways of finding these things. But again, if you need to find percentages, molar mass on the bottom and the amount of that particular element in the top. So for percent carbon, it was 12 in the top divided by 44. For oxygen, it was essentially 32 divided by 44. There's a whole series of nitrogen oxide compounds, all right? There's N2O, there's NO2, there's NO, there's N2O4, and the list goes on and on and on. One of the compounds has a percent nitrogen of 46.67%. We can use this information to calculate the empirical formula of this nitrogen oxide compound. So in this, we only have nitrogen and oxygen, all right? It gives us the percent nitrogen, so you can find the percent oxygen. See if you can use that information to find out which of those is the empirical formula of this nitrogen-oxygen compound. So pause the video, work on it, and unpause it when you're ready. Okay, I'm going to assume that you've worked on this question and you've got an answer. You want to check it out, and that's fantastic. Before we start, first of all, percent oxygen will be 100% minus 46.67%. So that number, whatever it is, that's going to be the percent oxygen. And the other thing is that all of those formulas listed, those are formulas based on moles. They're not based on mass. So in a problem like this, you've got to turn percentages into grams because they're mass percentages, and then grams into moles. And you can compare the moles that way to see what's happening. So let's do the nitrogen as an example here. You would take 46.67 grams. I am a big believer that you should just assume you have 100%, and that means 100 grams. So 46.67% nitrogen would be 46.67 grams of nitrogen. And we're going to take that grams of nitrogen and divide by the molar mass of nitrogen, which is roughly 14.01 grams per mole. And that's going to give us the moles of nitrogen we have. Now we're going to do the same thing with the oxygen. So it's about 53-ish%. Oh, you can do a better job than I can, but 53-ish% oxygen would be about 53 grams. We'll take that number and divide by the 16 grams per mole molar mass of oxygen to find the moles. Now, if the moles of N and the moles of O are about the same, then that means it's 1-to-1, and answer B would be right. On the other hand, if the moles of oxygen are twice as big, like if N was 0.5 and O was 1, then we'd have something like answer C. So we can use those mole ratios to figure out what's happening. So let's look at the math and the answer. First of all, the answer is answer B. It's 1-to-NO, nitrogen monoxide. Here is the 46.67% turned into grams. So 46.67 grams. And you want to turn it into moles. So you divide by 14.01 grams per mole, and this is the moles of N. Now, percent oxygen, like we talked about, 100% minus percent nitrogen. And that did come out to be about 53%, 53.33. Let's turn that into grams. So in 100 grams, that would be 53.33 grams of oxygen. Turn it into moles by dividing by 16 grams per mole. And this number is the moles of oxygen. Now, these two numbers, the moles of N and the moles of O, you can make a cheesy formula. N.3331 to O 3.333, but man, is that an ugly formula. All right, that's way too ugly for chemistry. So you need to break it down to whole numbers. You divide the bigger by the smaller. 3.331 is certainly is a little bit smaller than 3.333. So you can see that 3.331 divided by itself is exactly 1, and the other one is almost exactly 1. This is 1 nitrogen to 1 oxygen, or NO. Now, this is just the empirical formula. There is another step we'll talk about in a little bit where you can go from empirical to molecular formula, but this is the process, all right? If you have mass percentages, you first assume 100 grams, turn them all into moles, compare the moles to find the empirical formula. So this process works really, really well. We have 6.54 grams of zinc, and we're combining it with oxygen, and it makes some type of a zinc oxide, ZnXOY. And the zinc oxide, this white powder, has a mass of 8.14 grams. And we're going to assume here that all the zinc reacts. We can use this information to find the empirical formula. So what you should do on this problem is think about how to isolate the grams of zinc that reacted and the grams of oxygen that reacted. And if you turn those numbers into moles, you can compare the moles of O to the moles of zinc and see which of those seems reasonable. This is a good place to pause the video, and when you've worked through this problem, then unpause it and we'll talk about the answer. Okay, at this point, I'm assuming you've tried the problem and you've got an answer, so let's check it out, see how you did. In this problem, you want to find the moles of zinc and the moles of oxygen, and then you can compare them to each other to see which of those answers is right. Now, the zinc is easy. 6.54 grams of zinc reacted, and all of it was used up. So the first thing you want to do is turn 6.54 grams of zinc into moles of zinc. Now, the oxygen in this thing, 8.14 represents all the zinc plus all of the oxygen. So if you take 8.14 grams and subtract 6.54 grams from it, it's like all the zinc zinc and oxygen minus the grams of zinc, that's going to give you the grams of just the oxygen. And that's how you found the oxygen, 8.14 minus 6.54. And from there, grams of O to moles of O, compare the moles of O to moles of zinc to see which of those is the right answer. In this problem, when you do this, you should get answer A. But let's look at how we get this. So first you got to find the grams of O. 8.14, which is the zinc and the oxygen, minus the zinc, that number gives you the grams of O, 1.60. And from the grams of O, you can find moles of O. Here's the molar mass. You can do the same thing for the zinc, 6.54 grams divided by the molar mass of zinc. You also get moles of zinc, and notice, of course, they're the same number. And that's exactly the same number, so there's really silly to compare, but I want you to see that just in case you have to if the numbers aren't the same. 1 zinc to 1 oxygen, the answer is zinc oxide, ZNO. Now, if you thought about the charges on the periodic table, you maybe didn't need to do this problem at all, or you could at least make a strong argument for what the answer should be. Zinc is one of the stairs. It's a positive 2 metal. And oxygen, when it's an oxide, oxygen's in group 6, 6 minus 8, oxide is also negative 2. So when a positive 2 zinc and a negative 2 oxygen come together, they will be 1-to-1 ZNO. Now that's not definitive proof, but that would be a strong argument for why answer A is correct. And as you can see, answer A was correct. Woohoo! So anyway, life is good. But it's another way to think about if this kind of makes sense. Glyceraldehyde has an empirical formula of CH2O, and it has a molar mass of 90.08 grams per mole. And the question is, what is the molecular formula of this compound? And you've got 5 possible answers. So what I'm asking you to do here is how to go from an empirical formula and a molar mass to the molecular formula. This is a good time to pause the video and work on this problem. And when you're ready, when you have an answer, you can unpause it and we'll talk about what the answer is. Okay, I'm assuming you have an answer now to this problem and you want to hear it, so let's see how you did. An empirical formula is the smallest whole number ratio of atoms, all right? And the molecular formula, which is kind of like the holy grail of chemistry in this section, is the actual number of atoms in the molecule of the compound. So the answer here is going to be CH2O multiplied by some factor. So if you look at the answers, then A would be CH2O multiplied by 1, and that's legit. On the other hand, B is CH2O multiplied by 2. That would be C2H4O2, so that would be fine. Answer C is CH2O, the empirical formula, multiplied by 3. Answer D is CH2O, the empirical formula, multiplied by 4. But there's no way that this answer will be E, because E is not CH2O multiplied by some whole number. The hydrogens are wrong, all right? The carbon and the oxygen's fine, but hydrogen's not fine. That pulls the whole answer out. And what you need to do on a problem like this is you need to find the molar mass of the empirical formula. And the molar mass of the empirical formula might be the same as the molar mass of the whole compound, and it might not be, but that's what you need to do. Now, carbon about 12 grams per mole, hydrogen about 1 gram per mole, and oxygen about 16 grams per mole. So 12 grams per mole from carbon plus about 2 grams per mole from the 2 hydrogens plus 16 grams per mole for the oxygen. 12 plus 2 plus 16, that comes out to be 30 grams per mole. And 30 grams per mole, and again, you can do a better job on with your calculator and stuff than I can off the top of my head, but it's about 30 grams per mole, and that number is certainly not 90.08 grams per mole. So to find out how many empirical formula units go in your molecular formula, you would take the molar mass of the whole thing, 90.08, and divide by the molar mass of the empirical formula, which, as I said, is about 30 grams per mole. And you can probably see that's going to be a ratio of about 3. So let's go back and look at it. This number, 30 grams per mole, which is what I used here too, 30 grams per mole is the molar mass of the empirical formula of CH2O. There's the C, there's the 2 hydrogens, and there's the oxygen. The molar mass of the whole thing, 90.08, divided by the molar mass of the empirical formula will always give you a whole number. And that's why it's okay to be a little cheesy here. So this ratio, pretty gosh darn close to 3. So you're going to take your empirical formula and multiply it by 3. So the answer here would be C, C3H6O3. That is going to be the molecular formula. And again, you can go from the molecular formula back to the empirical formula, C3H6O3. If you divide each of those numbers by 3, that's where the CH2O thing pops in. That's why that is a reasonable answer. Molecular formula has to be empirical formula times some number. Now, sometimes empirical and molecular formulas are the same, and that's legit as well. If we would have found that the empirical formula's molar mass was equal to 90 grams per mole, then we would have said, okay, empirical and molecular formula are the same. But in this case, it was a 3-to-1 ratio. That's why we multiplied the empirical formula by 3. Here's a question. We have a compound with phosphorus and fluorine, and it's 75.41% fluorine. Stop right there. Percent phosphorus will just be 100 minus 75.41. This happens a lot of times. Chemists are too cheap to buy all of them. I don't know. But anyway, no problem. Anyway, after that, it says there's a molar mass of 251.94 grams per mole. 251.94, that's the molar mass of the whole compound. We can use this information to calculate the molecular formula of the compound. And there are 5 possibilities here. Now, this problem is basically a summary of the last couple problems we've done. You first want to find the percentages of P and F, and then turn them into grams, assume 100 grams, turn them into moles of P and F, and then compare them, all right? And you should get an empirical formula, some kind of PXFY, if you will, doesn't matter. Whatever thing you get, find the molar mass of the empirical formula and compare it to the molar mass of the whole thing, 251.94. That will be a whole number ratio, and that will be the number you multiply your empirical formula by to get the molecular formula. So all things we've done already, this is just everything all in one. Work on this problem a little bit. Pause the video, and when you're ready, unpause it, and we'll see how you did. I'm assuming that you've worked on this problem. You got an answer. Let's see how you did. So again, the idea here is first you want to find the percentages of P and F. You've got F, so 100% minus 75.41. That would be the percentage of phosphorus. And then those two numbers you want to turn into grams. I would assume 100 grams, so that means 75.41 grams of fluorine, because that's the percentage. Grams into moles. Compare the moles to find the empirical formula of the PF compound. And after you find the empirical formula, then find the molar mass of that. So add up the P's and add up the F's. If it equals 251.94, then your empirical formula and molecular formula are the same. On the other hand, if it's not, it's going to be a whole number ratio, and that whole number is what you need to multiply the empirical formula by to get the molecular formula. So there's a lot of math on this one. Let's start with the answer first of all. There's that part. The answer on this one is just going to be E. It's P2F10. So let's look at the steps here. I assumed 100 grams total, and 75.41% fluorine became 75.41 grams of fluorine. I turned it into moles, molar mass of fluorine about 19, 3.969 moles of F. Now, percent phosphorus wasn't given explicitly, but it's easy to find. 100% minus percent F equals percent P. There's only two elements here, 24.59%. And in 100 grams, that would be 24.59 grams of phosphorus. Turning it into moles, using the molar mass there of P, 0.794 moles. So we have a formula, but it's really ugly. 0.7940 moles of phosphorus for every 3.969 moles of fluorine. Pretty ugly. Divide both numbers by the smaller number. 0.7940 is certainly smaller than 3.969. So 0.7940 divided by itself is 1. That means 1 phosphorus. And 3.969 divided by 0.7940 comes out to be 4.999. That's pretty gosh darn close to 5. So the empirical formula of this compound, PF5, all right? Now that we know the empirical formula, our answer will be PF5 or P2F10 or P3F15, some integral of PF5. And to figure that out, we first need to find the molar mass of the PF5. So if you add up 1 phosphorus, 30.97, and add 5 fluorines, 5 times 19, you get this 125.97 number. That's the molar mass of the empirical formula. The molar mass of the whole compound, 251.94, divided by the empirical formula's molar mass, comes out to be a ratio of 2. And again, this ratio is going to be a whole number. So in this case, we'll take our empirical formula, PF5, and we're going to multiply it by 2. So that's where the P2F10 molecular formula comes from. If you have this down, you are good to go with the first midterm, all right? This is kind of the holy grail for chemists. So being able to knock these problems out is really important. If you did get stuck in anything, just make sure you know what to do, and you can go back later, look at other examples, practice and stuff. Will make this perfect. It's not a hard process to do. You just need to kind of work with it a little bit. And of course, if you have questions on anything, please let me know. I'm more than happy to help. Here are 5 compounds, and I'd like you to tell me which of them represents iodous acid. Now, all of these compounds are acids, and H is listed first, and all of them have iodine in them, but only one of them is iodous acid. See if you can figure this out. Pause the video, and when you have an answer, then unpause the video, and we'll talk about the actual answer. Okay, I'm going to assume that you have the right answer, or the answer figured out, excuse me. Let's just talk about how you did, all right? So a couple of things. The first acid there, HI, doesn't have any oxygen. So that compound is going to have a hydro prefix. And for HI, that's going to be hydroiodic acid, all right? So things without oxygen have a hydro prefix. But the other 4 all have oxygen with it. So really, to get started on these, you need to figure out which of them is the most common version. And if you think about Nick the icky camel, or whatever that expression is, icky is the key. You can also, of course, just memorize it. But IO3-1 is iodate, and that's the most common polyatomic ion. So if we were talking about polyatomic ions, IO3- is iodate. IO2- in C would be iodite. In B, you have IO-1, that's hypoiodite. And on E, you have IO4-, that's the periodate ion. However, we're not really talking about polyatomic ions, Russell. So the common polyatomic ion leads to an ic acid name. So on D, which is the most common, all right, the iodate is turned then as an acid into iodic acid. So HiO3 is iodic acid. And if you take away one oxygen from the common acid, iodic acid, that's when you end up with iodous acid. So the answer here is going to be C. C is iodous acid. Iodic acid comes from the most common one. Notice the pattern. You add an oxygen per iodic acid. Iodous means you take away an oxygen. Hypoiodous acid would having only one oxygen. And again, if you have no oxygen, you'll use the hydro prefix. Which of these is the correct molar mass for nickel 2 nitrate hexahydrate? So this is an example of a hydrated compound. And what I'd like you to do is, of course, first figure out what the formula for nickel 2 nitrate is, nickel 2 hydrate hexahydrate more specifically, and then from there you can figure out the molar mass. Make sure you add in the waters, the hydrates, when you're doing this molar mass. All right, this is a good place to pause the video, and when you're ready, unpause the video and we'll talk about the answer. I'm assuming that you've worked on the problem, and let's see how you did. This problem, we first need to figure out what the formula is for nickel 2 nitrate hexahydrate. Now, nickel Roman numeral 2 means nickel plus 2, and nitrate, a polyatomic ion, is NO3 with a -1 charge. So nickel 2 nitrate would have a nickel plus 2 and 2 -1 nitrates. So the formula would be NiNO3 2. Ni parentheses NO3 2. And that's because nitrate is -1 and nickel is a +2. So you need 2 -1s to balance it. However, this is also a hydrated compound, which means some of the waters kind of glue themselves on, if you will, to the central part. The hexa is the key to telling you how many waters, and hexa is 6, the Greek prefix for 6. So what this means is you have Ni parentheses NO3 parentheses 2, that's the nickel 2 nitrate, with 6 waters, dot 6 H2O. So that's the formula for nickel 2 nitrate hexahydrate. So when you do the molar mass, you want to add 1 nickel, 2 nitrogens, N times 2, 6 oxygens, this is just from the nitrate, by the way. So 1 nickel, 2 nitrogens, 6 oxygens. And for the water, you would have 6 times 2, 12 hydrogens, plus 6 times 1, 6 oxygens. So there's a lot of things to add up there. But when you do this, the answer comes out to be about 291 grams per mole. And again, there's the formula written out a little nicer there that I did. But anyway, hexahydrate, 6 waters, nickel 2 nitrate, -1 nitrate with +2, good to go. Okay, that's the end of the review for the first midterm. I do appreciate you spending your time with me. If you'd like more practice on things, there's lots of ways to do that. Online and in the companion, if you have it, there are practice problem sets. Practice problem sets went over problem sets 1, 2, and 3. There's practice problem sets 1, 2, and 3 as well. Practice problem sets have the answers at the end, so that's a great way and stuff to see. Concept guides and chapter guides are also helpful. Concept guides are both in the companion and online. They're worked problems that go through the different concepts from the different chapters. Chapter guides are online only. It's basically a digital list of all the things that might be able to help you, and I do encourage you to check it out. At the end of each of the chapters, definitely chapter 1 and chapter 2 of our textbook, and also some at the end of chapter 3, even though we're only looking at 3.1 and 3.2, I do encourage you to look at the end of chapter problems. Every other question has an answer at the end, and those are cool ways to start learning the things too. I do wish you the best in your studying. I definitely wish you the best with your midterm. If you have questions on anything, please reach out to me. Good luck with your studying.